recap of what we have discussed, and we are going to move on to something called the maximum likelihood estimation in this one. And we shall see how we use partial differentiation, how we use Lagrange multipliers and stuffs like that. Okay, so let me just write it down. Limit tends to infinity, probability of theta n cap minus theta. Theta is the parameter which theta n cap is estimating, of course. Greater than equal to epsilon is equals to 0. So we say that theta n is a consistent estimator if the following property is satisfied, right? Now obviously we also defined that MSE of theta was simply equals to expectation of theta n minus theta, actually theta n's MSE squared, right? Then we see that if limit n tends to infinity, MSE of theta n equals to 0, then theta n is consistent. This is another property. We can prove it as follows. We see that and this thing right here, we can obviously understand that this is less than or equals to the variance and bias, right? So what we can do is as follows. This is by Chebyshev's inequality, but the above thing is just MSE of theta n, right? And this would be 0 because we know that limit of MSE of theta n is also 0. And if that happens, theta n is again a consistent estimator. Now that being said, what we would like to do now is this maximum likelihood estimation. Now what is a maximum likelihood estimation? Well, obviously when we have an MLE, we also call it MLE. When we have an MLE in form, what we do is usually estimator for a random sample is given by, so this random sample is given by, so this is our maximum likelihood estimator defined, and we do this like this. So we take the product of the PDFs basically, and the PDF is dependent on some parameter theta which we are estimating. So that's how we do it. So we are trying to estimate the probability or the value of theta for which the likelihood is maximum. Okay, so that is what we are going to expect here. Now, how do we evaluate this sum? Well, obviously, now we turn back to our calculus days and we remember that we can take logarithm on both sides. So, and taking the logarithm of this would give us, right? And what we can do is we can define this one as, let's say, log of capital L, and log of capital L is equal to this, and we need to maximize log of capital L. So differentiating both sides, we have, so firstly the question asks us how do we differentiate both sides, right? So, well, it's obviously L prime by L, and we are differentiating it with respect to theta, of course. Okay, so since we are maximizing theta, we are differentiating it with respect to theta, and differentiating, you get something like this. Comma theta. Therefore, L prime is equals to xi theta divided by fxi xi theta, and this is equal to 0. And when this is equals to 0, we can find out certain values of it. So whatever theta we get, is called theta mle, which maximizes the likelihood. And we sure would see some example here, and that example would be this. The example is crucial to understanding what we are doing, because otherwise we would never know how to apply it. So the example is, suppose I'll just write down the question first. So we have observed the random sample x1 x2 all the way up to xn, and suppose we have that this xi belongs to normal distribution of theta 1 comma theta 2, right? So what we need to do here is we need to find out the estimators for theta 1 and theta 2, and we also need to find out the maximum likelihood examples. Okay, so what we need to do here is obviously the PDF for all the xi's given the two estimators theta 1 and theta 2, or the two parameters, is given by 1 by root over 2 pi theta 2 e to the power minus xi minus theta 1 squared by 2 theta 2. Now let us find out the actual value and let us see how do we do it. So the likelihood function, to find the likelihood function, we see this is the expression, right? And with this expression we see that we can write this as product of I equals to 1 to n, and this L is basically the likelihood function which we will be defining now, and well in the upcoming examples as well we are going to use the same likelihood function for x1 up to xn, and it doesn't matter how many parameters are there, we can estimate them all. So this gives us this would be, since the 1 by root over 2 pi theta 2 is a constant independent of I, we see this is equals to 2 pi theta 2 to the power minus n by 2, and the exponentials are all the product of two exponentials simply adds up the argument, so it's basically exponential of this, right? Now therefore taking the logarithm on both sides, ln of L should be equals to minus n by 2 ln of 2 pi theta 2, not a plus actually because we have exponential of minus, so exponential and logarithm are inverse functions, so log of exponential is just whatever is the argument, so minus right? Now to find out the expressions and the maximum likelihood expressions for theta 1 and theta 2, we need to do them one by one. So let us start with theta 1. Starting with theta 1, we have, and obviously all the derivative formulas and stuff and integration would be required here, so that would be embedded with this video for your forsaken needs. This would be 0, while this would be 2 times therefore this gives us L prime by L equals to minus 2 I equals to 1 to n xi minus theta 1 by 2 theta 2, right? And setting L prime equals to 0, we have we see that summation of I equals to 1 to n xi minus theta 1 is equals to 0. This means that n theta 1 is equals to I equals to 1 to n xi, or theta 1 is just 1 by n I equals to 1 to n xi. Therefore the MLE has been found, and it is 1 by n summation of I equals to 1 to n xi, which is just the sample mean. Now let us do the same method for part 2. Now the first term was minus n by 2 log of 2 pi theta 2. This one would be useful here, and thus we have minus n by 2. Differentiation of log of 2 pi theta 2 is basically 2 pi theta 2 2 pi, and this one the only term here is 1 minus 1 by 2 theta 2, which would be basically minus 1 by theta's differentiation is 1 by 2 theta square. So this term 1 by 2 theta 2, so this minus 1 by theta 2 will only be differentiated, right? And this is theta 2 to the power minus 1, and when differentiated this will become minus 1 to the power theta 2, so basically it's 1 by theta squared. So this would be plus 1 by 2 theta 2 squared I equals to 1 to n xi minus theta 1 whole squared, because this term acts as a constant, right? And therefore L prime by L is minus n by 2 theta 2 plus 1 by 2 theta 2 squared I equals to 1 to n xi minus theta 1 squared. Setting L prime equals to 0, we have therefore and this is just sigma square, right? Therefore we see that theta 1 mle is just x bar, while theta 2's mle is sigma squared. And this is how the likelihood is calculated. So we see a lot of examples of differentiation here, and this would always obviously be embedded with it. But then again, we need to practice this more and more so that we get to understand what are the key topics here. Obviously, in the next videos, we shall talk about more about how to do certain distributions and how to do certain things. But before that, you need to watch all the necessary content you need in order to understand all of this stuff. So be sure to clear your basics for integration and differentiation every time, because in every video we've embedded it, and that is required because each one of these videos are equipped with a lot of heavy differentiation and integration stuff, and that is why we have focused so much on integration and differentiation, and we have covered a lot of details in that as well. So we are going to find the derivative of a function f which goes from r squared to r, and it is defined as f of x comma y equals to a to x plus y, and inside we have g, so we can call it, let's say, gt dt. Okay, and g is basically an integrable function which is continuous from r to r, so it's continuous, right? So we need to find the derivative of this function f. Now notice that it is not a very usual problem as regards to the previous problems that we have solved, because this one involves integration, and when we are solving such a problem, we need to be keep reminded of that when you are doing an integration but with variable limits. Let's say in this integral the limits are from a to x plus y, where a is a constant surely, but x plus y, it's the variable in touch, right? It's the variable in discussion in the variable f. So in the function f, the variables of importance are x and y, and in the integral they're defined as the limits of some function. So x plus y could be some function h of xy, but they are there, right? So that's how the integral is dependent on the variables. Now how do we find the derivative of it? So it's no different than to find a derivative of a different function composed of x and y, and we can use our same methods to do that. So what we can do is as follows. We can say that h of t is a to tg, integral of a to tg, and we don't really need to understand how the x plus y function works, okay, because h would be the first function and then would come x plus y. So what we can do here is we can write f prime of x comma y as, firstly we are going to find out this h of x plus y's derivative, right? Now due to the chain rule we have df a comma b, so the derivative at the point a comma b would then be equal to dh of a plus b, firstly. So this is how we are going to do it, multiplied by pi 1 plus pi 2 derivative at the point a comma b. So this is basically dh of pi 1 plus pi 2 at a comma b multiplied by pi 1 plus pi 2 whole prime a comma b. Okay, now the derivative of h can be found out from the basics of calculus. So the fundamental theorem of calculus says, the fundamental theorem of integral calculus rather, now, if you remember, we had done this back in the course where we had done integral calculus. I have defined this kind of functions there and how to do this kind of limits. Such a video would also be included at the end, so that you don't need to don't need to go to a separate video to understand that facts. So you might as well learn it here. The fundamental theorem of integral calculus says that so if we were to differentiate d dt of a to t g, let's say gx dx for example, then this would just give you g of t. This is because we are really here trying to state the facts that g of x is basically inside the integral, which means the answer to this integral a to t g of x dx would be a function whose derivative is gx, right? So gx is continuous and it is integrable. That means there exists some function. So let me write it down clearly. Since it is continuous, it is integrable. So there exists some function p of t in a comma t such that p dash t is gt. Okay, and this would give and this would actually give that since there exists some function, we can write that a to t g of x dx is simply equals to a to t p dash x dx, and this would give you p of t minus p of a. And now differentiating both sides with respect to t, we have a to t g of x dx is p prime t, right? So this is the whole thing we wanted to prove. Now coming back to our problem, we see that df ab is basically, now dhab as we had pointed out is g of at, right? So it basically becomes g. So here we had dh of pi 1 plus pi 2, and we understood that h of t is the integral is basically g of t, differentiation derivative. So d of h of pi 1 plus pi 2 ab is basically d of h of a plus b, which is basically g of a plus b, right? So this becomes g of a plus b multiplied by pi 1 prime plus pi 2 prime a comma b. This becomes g of a plus b and 1 comma 0 plus 0 comma 1 a comma b. So g of a plus b times 1 comma 1, which is g of a plus b comma g of a plus b, which is the derivative for f at the point a comma b. So this would sum up the answer. So as you can see, like, this answers are pretty much constructed from the basics, and they also themselves consist of the basics. They do not really concern with themselves a lot of different and complex results, but rather interesting results. Like, we have used the fundamental theorem of integral calculus here. We use the same definitions of linear basis of like pi 1 and pi 2, because there were two variables, so we used pi 1 and pi 2 and stuff like that. So all in all, these questions are more about how you can apply those formulas and rather less about how to memorize them, because these results just should come generally to you. It just should be instantaneous to you that what to use in a certain situation depending on what the question asks you. So as you can see, the question asks you here explicitly to differentiate an integral, and the integral has a variable in it, in the limits. It should be directly clear to you that, well, the integral is basically the inverse function of derivative. So if I am to basically differentiate an integral, it should give back the function, right? Now the question remains, what is the function actually going to come out? Is it the same function? Is it something plus an argument, or the argument is changed, or something like that? So for that we use the fundamental theorem of integral calculus. Anyway, so that would complete this answer. Let us go to the next problem. So that's the problem we are going to solve. It is said that given a function f belonged f from r to r squared to r, defined by f of x comma y from integral of a to xy. Xy means here x dot y, which is the dot product between two vectors, because you see x and y are two-dimensional vectors. And then the definition follows, and then we have to find the derivative of f, and g is basically a real function and it is continuous. So I'll give you 10 seconds to try and think about this problem based on what you have done, whatever we have done in the previous one. So I think that should be enough time. Now, to do this problem, we need to be careful about a certain number of things. Like, there is the dot product, and the dot product needs to be carefully investigated. Now, how do we investigate the dot product? So if you remember from previous exercises, we can write as follows. So this basically is the composite definition, right? Where t of course is the variable, and pi 1 and pi 2 are your usual linear transforms in two dimensions. And we would like to find out how to find the derivative of this, but this is very much easy using the chain rule. Let us try to do it. So using the chain rule, we have we do have this df at the point a comma b is basically derivative of a to t g at the point a comma b. Basically this is not quite it, because what you want to do is this of pi 1 cross pi 2 at the point a comma b multiplied by derivative of pi 1 dot product pi 2 at the point a comma b. So how do you evaluate this? Well, obviously, even evaluating this integral, this particular function, the first part is pretty trivial because of the last problem as well, where I had exactly defined how to find the differentiation of an integral whose integrand is continuous in the interval, and it's also defined at the endpoints. So since it is continuous at all r, so it's defined at all endpoints, obviously. So this would just be g of a dot b, which is a dot product b, multiplied by, now this product's differentiation is basically pi 1 prime pi 2 at the point a comma b plus pi 1 pi 2 prime at the point a comma b. This gives you g of a dot b multiplied by 1 comma 0 b plus a into 0 comma 1. Therefore this gives you b comma a, and therefore what you can do here is you can write b into g of a dot b comma a into g of a dot b, which is our required answer for that derivative. So you see that these problems are mainly shaped by the fact that you just need to consider two-dimensional or three-dimensional, whatever it is, you just need to consider them, and then you need to have a perfect way to define them as a composition in order to use the chain rule. So the chain rule is the only way you can evaluate this kind of derivatives, or all the derivatives for that fact, and that's the easiest way, of course. So well, using that we can always find out this kind of derivatives easily, right? Okay.